Hi everyone, welcome. The topic we're doing today is current, which is the second part of current, and we will concentrate in Kirchoff's law, meter bridge, potentiometer, and Wheatstone bridge principle. So, without much delay, we'll start.
So what I have here is something that represents a piece of wire with a charge carrier in it. And it's not going to have any kind of flow in one direction or the other because there's no difference in the electrical potential at each end. However, if I make perhaps one side positive and the other side negative, and then this figure here is going to represent the conventional current. The conventional current is a flow of these charged particles, and in this case it's going to move from positive to negative. Now inside the battery we have various chemicals here, and what they do is they cause a difference in the electrical potential between one end and the other. And if we connect this up into a complete circuit, what we tend to do then is have a different electrical potential at each end, and therefore we have the flow of charged particles, which means we have a flow of current. So here we have a very simple circuit, and what we have is the terminals. We have the positive and the negative, and by convention we have current that goes from positive to negative, so that's conventional current. Now this is our source of energy, and what I'm going to do is I'm going to represent the energy with these little yellow blocks here, and effectively inside the cell we have some chemical energy, so I'm going to leave that there. Now this is a bit of a dull circuit at the moment, so I'm also going to add some kind of components, and here we have a filament lamp. Okay, it's not quite perfect, but it's all I could do in Lego. So what we're going to look at is, if we have this very simple circuit, effectively a cell and a light, we're going to look at this flow of energy and where it goes in that circuit. So we have this store of energy at the cell, and over time, provided there's a current flowing, this energy is going to be transferred around the circuit and it's going to be emitted at the light that we have down here at the bottom. And in order for this energy to be transferred, what we need are these charged particles. And effectively what they do is, as they leave the cell, they pick up a small amount of energy, and the charged particles move, and this is then the electric current. And as they move around, they transfer this energy from one point in the circuit to another. When they get to the cell, what they do is they release the energy and then they keep on moving. So the green man here is a bit like the electric current moving around the circuit. As it goes past the cell again, it's going to maybe pick up a bit more energy. And obviously you can see this analogy isn't perfect, but effectively what these do is this current is going to move around and it's going to transfer energy from one place to another in that circuit. So what we have across the cell is an EMF. Now an EMF, which stands for the electromotive force, even though it's not actually a force, this is the amount of energy transferred from chemical energy into electrical energy per unit charge. And this often has a symbol capital E, or sometimes it's also sort of like a curly E or an epsilon. And the units for this are the volt. So EMF is the energy per unit charge transferred from chemical energy into electrical energy. So as this flow of charged particles per unit time, or a current, flows around the circuit, what happens is they then release their energy when they get to a component. Now this charged particle is going to transfer its energy from electrical energy into other forms, and it does it across this component. And what happens is the energy is emitted, and what we have now is the potential difference. Now the potential difference is the energy transferred per unit charge from electrical energy into other forms of energy. And here we have that potential difference. Now the important thing to note is that this charged particle will keep moving around the circuit. And if we think about Kirchoff's first law, we can say that the current at any point in this circuit is going to be the same, because we just have this very simple basic series circuit. So this is one kind of analogy that you can use to maybe think about what's happening in the circuit. As the charged particles move from the one terminal of the cell to the other, they're moving around the circuit, and this flow of charged particles here, which is the electric current, what they're doing is they're picking up energy at the cell or the power source, and it's been converted from chemical into electrical, and therefore we have a source of EMF. As it moves around the circuit, when it gets to a component, it releases that energy and it transfers it from electrical into other forms, and therefore we have a potential difference across that component. There's going to be a difference in the electrical potential between this side and this side of, in this case, a filament lamp. Now the current will still flow, the charges still move around the circuit, but what they're doing is they're transferring energy from one place to another. So how do we measure the potential difference? Well, what we can use is a voltmeter. Now, a voltmeter must go in parallel with the component we're measuring, because effectively what we want to do is look at the difference between the electrical potential here in the circuit and over here. And we do that with a voltmeter, which has this symbol here. And the important thing about a voltmeter is it must go in parallel. And in order for it to basically have no part in the circuit, it must have a very high resistance. The reason for this is we don't want the current to be basically flowing in and through this component. We want all the current to be going through this component, and therefore we kind of block off the current going through this with a very high resistance. So this voltmeter will go across a component in order to measure the potential difference. And again, we measure the potential difference in volts, pretty obvious from here. And this is very different to an ammeter. An ammeter goes in series and it's measuring the current through a position, whereas a voltmeter is measuring the difference in the electrical potential across that component. So just to summarise then, what's the difference between EMF and potential difference? Well, although they're both measured in volts, the EMF is, if we think about the energy, it's going to be the energy per unit charge that's transferred from chemical to electrical. Whereas on the other hand, the potential difference is the energy transferred per unit charge from this electrical energy into other forms. So that's it, the difference between EMF and PD. And just think about it in terms of the energy per unit charge and how the energy is transferred from either one form to another.
We have to do Kirchoff's law first. So let's start with Kirchoff's law. It's Kirchoff, they say. So Kirchoff's law. These are two laws. The first law is always called as junction rule. And it's also called as KCL, which is Kirchoff's current law. It's based on law of conservation of charge. So these are the very important information you should know. Conservation of charge. So these information you should know. It's also called KCL, Kirchoff's current law, and it's based on law of conservation of charge. So what does this say? Let's consider a junction. Junction is a point where current will meet or move. You can say a junction is where some trains will come, they will go out. It's a meeting point, basically. So this is your junction. J, let's take. And now some currents are coming in, some current is going out. This way. So arrow mark inwards is coming in, going out is that way. So let's name it as I1, I2, I3, I4. According to your Kirchoff's first law, the algebraic sum of all the currents in a given junction is 0. Or to make it simpler, in terms of charge, if you ask me now, the amount of charge entering junction equal to the amount of charge leaving junction. So you can't have any charge in the junction now. So the charge entering will be equal to charge leaving. So there are current entering, there are current leaving the junction. And if you add them up, the answer should be 0. So according to the law now, the addition of all this is 0. And if you want to get 0, you can't have addition, subtraction, division. So what we do is there's a sign convention for this. The sign convention is very simple. Current coming towards junction is taken as positive, and current moving away from junction is taken as negative. Current coming towards is this is coming towards, this is positive. This is coming towards, this is positive. This is going away, negative. This is going away, negative. This is positive. So you write I1 positive plus I2 positive, I3 negative, I4 negative, and I5 positive should be equal to 0. The total current in a junction is always 0. This is your Kirchoff's current junction rule or Kirchoff's current law. Now, how to go about, how we use it in normal connection circuits now? This is a simple example I tell you, where you have to use junction rule. Imagine there are two batteries, and this is E1, this is battery E2. If you want, you can have internal resistance here, R1. You can have internal resistance here, R2. Now, this will send a current I1. So, current from the first battery is I1. Remember now, any current going out of the battery should be the same current coming back. So I1 goes, I2 comes back. Similarly, I2 will be going out, I2 will come back. So symmetry should be maintained. I1, I2 both are coming this. So I1 comes this way, I2 comes this way. They are meeting here to go as I3. Now this is my junction J. So at junction J, my I1 is coming towards, I2 is coming towards, I3 is going away. Use junction rule now. I1 positive, I2 is positive, I3 is negative, should be 0. Or I1 plus I2 equals I3. This is logical, we know that, because I1 and I2 has to become I3 now. So this is where they use junction rule in physics. So it's a very straightforward one. We have been using it before, but we don't know that we are using junction rule. That's the only problem. So junction is not an issue. Junction rule is not a problem. Now the second law of Kirchoff or Kirchoff, the second law is also called as loop law. This is based on, this is also called as KVL, Kirchoff's voltage law. So that was Kirchoff's current law. This is Kirchoff's voltage law. And it's based on law of conservation of charge. So conservation of energy. So law of conservation of energy. So that is charge. This is energy. Energy conservation, you know, energy cannot be created nor be destroyed. So we are using the logic of energy is conserved. That's what we're trying to do. Before doing that, we should know this, what we did before. We just see that and then we go for the law. What the law is saying. Let's imagine there is a battery of EMF E, interresistance R. There are resistors R1, R2, R3 and R4. This circuit clearly indicates one thing very clear now. There's a resistance here. There's a resistance here, here, here. That means all the other points made, there is no resistance offered at all. Resistance is actually collision of electrons. Collision is when a heavy particle have a collision, when they move, they slow down and lose kinetic energy. So whenever there's a resistance now, energy of electron is lost. So everywhere in the resistor now, depends on the resistance they have, energy is always lost. So this EMF, let's imagine, is 10 volt. Out of 10 volt, some voltage gets wasted inside the battery itself, because battery, if it's new, less voltage is wasted. But voltage gets lost inside the battery because of the voltage drop, which is going to happen here. Losses basically. And why we say voltage is dropping? Because voltage actually is working upon charge, which is actually joule per coulomb. So if you see logically, voltage is more of energy only. So whenever there's a loss of energy, there's a loss of voltage. It's a very simple logic. So this energy of 10 volt or 10 joule per coulomb, what they have, that when they, before coming out, is lost inside the resistor itself. So that may be, let's say, 1 volt. So out of 10 volt, 1 volt is got lost inside the battery. You have 9 volts left out. That's going to be your positive plate, which is called your terminal potential. That's okay, terminal PD. So this negative is always 0. Now 1 volt is lost, 9 volt is there. So imagine in this first you have 3 volt lost. Let's say 2 volt is lost here. 2 volt is lost here. So I got 1 plus 3, 4 plus 2, 7 plus 2, 9. So the total is 10. Here the left out 1 volt has to drop. So there is no option now. So clearly, if you see the voltage loss happening now, so there is a voltage drop of 1 volt. 1 plus 3, 4 plus 2, 6 plus 2, 8, and this will be 10. So 4, 6, 8, and 10. So if you see the total voltages now, the voltage was 10 volt was there, and all the 10 volt got dropped inside. That means the energy was 10 volt, all the energy has got lost. You are not saving anything, you are not gaining anything or losing anything, because energy cannot be gained or lost. It can be only changed in other form. So this energy of this is changed in form of heat, because when they have collision, heat is produced. It's like when current is passed through, heat is produced. So in a circuit, if you make current to flow, if you have a 10 volt battery, all the 10 volt has to be dropped inside the circuit. So if you add all the voltage drops, voltage drop is equal to IR. If you add all the voltage drops, let's take the voltage drop in this is IR1. The voltage drop in this is IR2. This is IR3, IR4, and IR. When you add them up, that's going to be equal to EMF. So the addition of all the voltage drops should always be equal to the EMF of the cell. and this is your Kirchoff's second law. So it's a very simple thing now. Whenever you have a circuit and you have a battery in the circuit now, if the battery voltage is something, all the voltage has to be used in the given circuit. You cannot gain or lose anything. It should be exactly the amount of energy loss is exactly equal to what energy you have. So the total voltage drop in the circuit, including the voltage drop inside the battery, if you total add them up, that should be equal to the battery EMF. Or if I take this towards the left side, minus E equal to 0. So the total current in a junction is 0 is your junction rule, and total EMF is 0 is your loop law, it is your voltage law. So Kirchoff's current law is total current in the junction is 0, and Kirchoff's voltage law is the total voltage or EMF in a junction is in a given loop is 0. So let's do this. Now what we have to do is simple. So what we do in second law, it's as simple as that. Let's take a circuit now. Let's have a circuit which is not a single loop, more than single. If a single loop is there, it's very easy to find the current because we have this much only. Then I have to find all the R and V by R is I can find it. But I need to have more complicated circuits now so that let's name A, B, C, D, E, and F. This interval is R1, this is E1, this is E2, this is R2, this is R1, this is R2, this is R3, this is R4, this is R5, this is R6. You see the current now? The current from this battery is I1, and I1 will come back to the battery. The current from this is I2, I2 should come back to the battery. I1 goes this way, I2 goes this way, they add up to become I3, which will be equal to I1 plus I2. Because we know junction rule, I told you already, and we'll go to adding it. So I3 is I1 plus I2 now, I2. So clearly I got a current I1 in this side, I got I2 here, I got I2 here, I got I1 here, but in between I got I3, which is addition of I1. It's like a person starts from his house in this direction, other fellow moves this way, they meet and say hello here, and they start moving together. So as they reach here, the person who's coming from this house will go back to his house, and this person will go back to his house. This is what happens now in current as well. The house they started will come, they come back, and the house they started came back. That's what has happened. So what we have to do is simple. First, when you're given a circuit now, draw the current. Current is given normally, so no issues. Current is already there. Then first see how many unknown currents are there. We have got two unknown currents. I1 is not known, I2 is not known. Because I3 I can add I1. So I1 is not known, I2 is not known. So I know I don't have two currents which are not known. So I will make two equations using Kirchoff's second law. So for two equations now, I take two closed loops. The loop should be closed. If I say closed, wherever you start, you have to go back to the same point where you started. For example, if I start from A, the loop should be A, B, E, F, and A वापस. So A में start करके A में वापस आएगा. That's going to be the loop, complete loop. Or you can take the complete outside loop like this. A, B, C, D, as a full loop and come back to it. So you cannot say my loop is B, E, F, not allowed. A loop means it should be a complete circle. That means where you start, it should come back to the same point where you started. It's a complete closed circle. That's what is called a loop all about. And you can take any direction you want. There is no story of putting arrow marks like this and say clockwise, anti-clockwise. Do not waste time on all these things now. You go for any way you see. So let's start. We'll take the loop A, B, E, F, A. So the first two of beginning is A, B, E, F, A. As I told you, remember, I started from A and went back to A. So this is what a loop is all about. You cannot be halfway stitched, 2.5. Now, what we do is simple. Wherever there's a resistor there, find the voltage drop. Voltage drop is IR. And wherever the resistance is there, voltage drop you find out, and you just sum up all the voltages. Add all the voltages now on that loop. So I have a voltage drop here, I have a voltage drop here, I have a voltage drop here, and here for this loop. If I don't have a resistor here, for example, the circle is like this given to you, then you start from A, nothing is there in A. So you will not waste time in doing anything else, but my first voltage drop will be here. So in Kirchoff's second law, you should be very sure about one thing now. In the loop, wherever resistance is there only you will take the voltage drop. And wherever battery is there, you take the EMF of the battery. That's what is the story, very simple logic. So I don't have a resistor here, so I'll not take anything. I don't waste my time, I'll just walk to here, and first voltage will be here. But I've already made it here, so let's make that now, as of now, R1 is here. So voltage is IR. So first, next thing you should know is see the current direction also and see what's the current flowing in the given resistor. R1 has got current I1. You can see that current I1 is coming in R1. In R2, the current is I2. In R3, the current is I3. In R4, I3 now is only up to this point. Now it's become I1 now, and this become I2 because they branched now. So R4 makes I1, R1 makes I1. So my current, I'm very sure about it. So I can multiply IR value. So I1, R1 will be the voltage drop in this. I3, R2 will be the voltage drop in this. I3, R3 will be the voltage drop in this. I1, R4, I1, R1 is what the voltage drop. But the sign convention is a big problem. Sign conventions, there are 2-3 ways of doing it now. So you can follow whatever is easier for you. What I'm doing, exact reverse also is there. So whichever is easier, do it. It's up to you. So what I'm doing is you just follow. If it's easier, then follow that. Now A to B. So our logic is very clear. Whenever you move with the current, I'm moving the current. For example, I'm going from A to B. Even current is also going from A to B. Whenever the current is with you in the same direction, the voltage drop will take is positive. So I1, R1 will be positive because myself and my current are in the same direction. Then I'm taking a turn from B to E. Even my current is also B to E. So plus I3, R2. I3, R2. Then I'm taking a turn from E to F. Even current is with me. So plus I1, R4. Take a turn, currents with me, plus I1, R1. So now clearly, all my currents are with me, so all the voltage drop is positive. So when I go in a loop, which way one battery will always come. So when I go in this direction, like this, when I hit the battery, see what plate I'm hitting. When I go in this direction, I will hit a negative plate. When I go in this direction, I will hit a positive plate. So I'm going this way. When I go this way, first plate coming is negative. Take that negative sign as a sign of EMF and write 0. So this is going to be Kirchoff's law for the first loop. So logic is simple. You see where's the resistor there. Do IR for that. If your I is with you, IR is positive. But your I is against you, your IR is negative. So this is what you hit it. And whenever you come across a battery, when you go in one direction, see what's the first plate of the battery which is coming to you when you cross. Whatever sign is there, take a sign for that. Or people, what they do, they go this way and they say since minus comes plus, okay, they take it that way, equal to. Okay, equal. So it's okay. That's not a problem. So normally people don't take minus, they take E that side. When they go that side, it's plus only. So they say when the battery, you jump from minus to plus, it's plus. When you go from plus to minus, it's minus. So you should write that side. So anything which is easier, you can do it now. This is the first loop I've taken. Let's go for the second loop. Second loop, let's make it a complete loop now. Let's take A, B, C, D, E, complete loop. A, B, C, D, E, F, A. Let's take a complete loop. So I'll start from this. So I'm going from A to B. Current is also A to B. So I1, R1. The first one is easier for me. But I'm going from B to C this direction, but my current is in the opposite direction. So you can see I'm going this way, but the current is in the ulta direction now, it's minus. It's minus I2, R5. Because I2 is the current, R5 is. So then I come here, I've seen the battery here. But when I come this way, the first battery plate is plus, so plus E2. Here, once again, current is against me, minus I2, R2. Here also current is against me, minus I2, R6. Then I'm going this way. So current is already is with me. You can see the current action with me, so plus only. So plus I1, R4. Current is with me. Plus I1, R1. And then I come here, minus plate comes first. So minus E1 equal to 0. So n number of points you take, n number of resistors you take now. The logic is very simple. If there's a resistor, take the voltage drop I into R, and your current is with you. It's positive IR, against you, negative IR. And when battery comes now, whatever plate comes to you first will be the sign of the battery. That's its logic. Now, this is what Kirchoff is all about. So Kirchoff's basics is this, and then you have to use max. Two equations you make and use max and then solve. Solution for that, for solving Kirchoff video is separate, we'll do. Now, but sometimes you have a problem. Kirchoff, the biggest problem is drawing current. For example, if they don't give current, what to do. It's NCERT question now. This is a 2 volt, 2 ohms. 1 volt, 1 ohm, 2 ohm, 3 ohms, 3 volt, 1 volt, 1 volt, AB. The biggest problem we're going to face now is how to draw current. There are so much of batteries, and normally current should be drawn from plus to minus. If there's a plus, now my current from this plate will be in this direction. But this plus current will be in this direction. For this plate, current in this direction. This how much current will go, wherever it goes, we don't know. But we know one thing, current always flows in one direction, and the bigger battery takes charge. So if you have any question based on a lot of batteries coming in a circuit now, the first thing you should do is don't get confused. Make current from only one battery. That means imagine there's only one battery, other batteries are not. For simplicity, you can take any battery you want. But for this thing now, let's take the bigger battery into consideration. Let's imagine this is the battery there, these batteries are not there. So I'm going to make current from this one. So there's a current from this I goes from here, I goes here. I may say one current branch as I1. Now here you can write I2. The problem in writing I2 is you will have three unknown currents I1, I2, so you make three equations. Always minimize to 2 as much as possible. It's not possible to go for 3. 3 is the maximum you can go for. So this is I, this is I1. That means imagine this is 10 amperes of current. In that 10 amperes, 2 amperes have now gone here. What will be the current in this now? Which will be 10 minus 2, 8 amperes. How I got 8 amperes? It's 10 minus 2. So that is I minus I1. So this is I minus I1 will be this value. So this is going to be I minus I1. And this is I means I will come down. So this is the current we have to find. You can take two loops you want. Let's take and find out how to do it. AB, let's take AB, DA. You start from A and I went back to A. See this, I got two A's here. Complete loop. You start from A, move. What I come across the battery ka plus plate. So write plus 1. Plus IR. I is I minus I1 and R is 1. So 1 into this. R into I. 1 into I minus I1. Like take it down. I'm going this way. The current coming opposite direction. So voltage drop is I1 into 2. That is 2I minus 2I. Minus because the current is in opposite direction. Now you go this way. D to A are going. Current is also D to A. Plus I minus I1 into 2. So 2 into I minus I1. Then I come across a battery. Minus 2 equals 0. So this is my first equation. Open the brackets. You get an equation in terms of I and I1. This is the first loop. Let's go for the second loop. Second loop, what we take is we take BC, DB. Let's take BC, DB. Start from B. My first voltage drop is positive. I with the current is with B. So 3I minus 3 because minus plate comes first. Then take a term plus 1. Then I into 1. I. Take a term. Current is with you. 2I1 equal to 0. Once again, you've got an equation of I and I1. Two equations now. Simultaneously solve it. You get current I and I1. Even I minus I1 value can be found out. So I can find current every branch. This one, this one, this one, everything can be found out. And this is an NCRT question. It's been asked in course a lot of times. The only issue here is the current direction is a problem. So you can ask me one thing now, what if my current direction is wrong? Or what if I've taken a smaller battery and made the current? There is no problem. You can take any battery and make currents now. If your current direction is wrong, then the answer will come in negative. Otherwise, your value won't change. For example, if your answer of I2 or I1 is minus 4A, that will clearly say the I1 you are drawn in the diagram is reverse actually. The current is going reverse. So there is no problem in Kirchoff's law that whatever you're doing now, the current logically, if you take, it's logically right. Even if your current direction is wrong, maybe the bigger battery is taking charge and the current is actually going reverse, no problem. The answer will come in negative, but the value magnitude will not get full. So Kirchoff, the answer may be in negative as well. So negative indicates the actual direction you are showing the diagrams is not the right one. The current is actually going the opposite direction. So this is the most easiest way to do it. So if you do some 10 questions in this, then you will be like, I can do it. So main problem is take your time to make your equation first. If your equation is written properly, then your maths is good. It's 10 standard maths. Basically, math because you will only take the side of this equation solve it, that you can do it nicely. The issue is one small change of minus plus, the whole numerical goes wrong. So be careful about it. Next is the Wheatstone bridge. So Wheatstone bridge we already studied. So still the Wheatstone bridge principle basically. Wheatstone bridge. So Wheatstone bridge you know already. There are 4 resistors in 4 arms of a given circuit. And in between there's a galvanometer connected now. And there will be a current flowing from the battery from here. And this is the EMF E. You can even have a resistor here, small r. So this is P, this is Q, this is R, this is S. So how the current flow basically, how to draw current? The current from here will be I. I has to come back. So always see to it that the current is same. This I branch into 2 parts, which is I1 and I2. I1 branch into 2 parts, I3. Oh, don't put I4. 3 unknown currents is only possible. So write this is I1 minus I2. As I told you, this is 10 amperes and this is 2 EVA. So you have trouble with I1 minus I2. I2 comes like this, I3 comes like this. They both meet here. So they will go together as I2 plus I3. Now I2 plus I3, I1 minus I3, I3 and 3 get cancelled. I1 plus I2. But I1 plus I2 is I1. If you take junction rule here, I equals to I1 plus I2. So I is I1 plus I2. So this I will be equal to I1 plus I2. Because here I is this junction here, I is towards these 2 away, I branch into 2 parts. So I1 I2 add up to become I and B. So logically you're right. Now I'm seeing current everywhere. There's a current in this, everywhere. The galvanometer will show reflection. But if in a potentiometer, in a meter bridge, if you adjust the resistance values and when your ratio of P by Q, this by this, equals R by S. So the ratio of these 2 arms and these 2 arms are equal, then the galvanometer will not show any reflection. Then I3 will be 0. So this is a very important information now. So in Wheatstone bridge, there are 4 resistors and in between there's a galvanometer there that's called a Wheatstone bridge. In that, when P by Q ratio and RMS ratio is equal, then the current through the galvanometer becomes 0. There's no magic here. There is no current flowing through this suddenly because the voltage at this point B and voltage at D becomes equal. So when voltage of B and D becomes equal, same potential, no potential difference, current stops flowing. So the voltage drops happening in these 2 matters and that depends on the current flow happening. So these resistors P and Q will decide the current flow in this, RS will decide the current flow in this. So the ratio decides how much current is flowing in these and the voltage drop is also there. So the voltage drop becomes equal, the voltage in this and this will be same. So automatically current flow will not happen. So this can happen only when P by Q is equal to R by S. When this happens, no current flows through. This is always called as the balanced condition of Wheatstone bridge. So Wheatstone bridge is balanced when P by Q is R by S. But you can't tell every time it's very balanced. So always remember now, when a Wheatstone bridge comes, you can't say I3 is 0. You can have a Wheatstone bridge with P by Q is R by S. You can have a Wheatstone bridge with P by Q not equal to R by S. If P by Q is R by S, my life is very easy. Remove the center part because there's no current only. Then these 2 resistors will be series, these are in series and parallel. You can find the normal condition, V by R is R. So there's no problem at all. But if P by Q is not equal to R by S, then there's an I3 coming into the picture. Then we have to use Kirchoff's law to find out the current I1, I2, I3. So your question gets complicated and you have to go for 3 equations to solve when P by Q is not equal to R by S. So whenever you are given a question in your paper, first check is P by Q equal to R by S. If it's equal, then no problem at all. Remove the center part and find out the resistance, the overall resistance and find out. If it's not, then tell yourself you have to go for Kirchoff's law and solve it. So that's a condition. So let's now imagine it's not balanced. So imagine now it's not balanced and let's do Kirchoff's second. And we take 2 loops now. So we'll take the first loop A, B, D, A. Now this is an unbalanced condition I'm taking. So current is still flowing everywhere. So I'll start from A and voltage drop and take second law. So IR, so I1P. I'm taking plus because current is with me. Then I take it down, current is with me, I3. Let's take the resistance of galvanometer to be G1. So I take GS, resistance of galvanometer, I take this one. So I come from B to C. Then I go from D to A. I'm going D to A, but current is coming from A to B. So minus I2R equal to 0. So this is my first equation, which is AB. Then I take BC DB. I'm going from B to C, current is with B to C. So it's going to be I1 minus I3 into Q positive. Then I'm going from C to D, but current is going from D to C. So minus I2 plus I3 S. I'm going from B to B, but current is going from B to D minus I3G equal to 0. So I'm taking two loops now. So you can see there is no battery. Because there's no battery in the two loops now. So there's no need to take battery values. You don't need it. But if you want to do numericals of Kirchoff's, third equation you should make with the battery and then solve it. Now, I'm going to prove the Wheatstone principle. So I'll not be using the third equation. So now in this we know P by Q is R by S, I3 is 0. Now let's go the reverse part. Let's imagine I3 is 0. Let's see what's happening. I3 0 in this will remove this out. I3 0 in this is gone. I3 0, this is gone. This is gone. And this is gone. So all the I3s are removed. So I'm left out with I1P minus I2R equals 0. Or I1P equals I2R. This is my first equation. Similarly, here it will be I1Q minus I2S equal to 0. Or I1Q equals I2S. This is my second equation. Now divide 1 and 2. 1 divided by 2. So you get I1P divided by R1Q equals I2R divided by I2S. I1 gets cancelled, I2 get cancelled. So P by Q is R by S. So that's what we have to prove. When I3 is 0, P by Q is R by S. Or when P by Q is R by S, I3 is 0. This is a derivation for balanced condition of Wheatstone bridge using Kirchoff's law. So this is derivation which came in board this year also. It's a very important derivation. So you should know your Kirchoff's property. If you know the second law properly, sign convention, if you're not confused, then it's nothing like that. You can do everything properly. So this is what you have in your Kirchoff's law, first and second law application. You can do a lot of questions in it. Practice repeat. Now next comes your meter bridge. This is a machine used to find unknown resistance of a given wire. Also we can find the resistivity of a given wire. We can find temperature of the resistance. We can do a lot of things. So for us, we are concerned about finding out the unknown resistance of the given wire. For example, I give you a piece of manganese wire or some wire. You don't know what the wire is also. Let's imagine now I've given you a piece of wire, which is a resistance wire. You have no clue what it was. You can find the resistance of the wire, you can find the resistivity, and tell me exactly this is a manganese wire or a constant wire or a nichrome wire, because every value of constant in nichrome is constant value. So if you know the resistivity value, that's a constant value of that. So you can take it from the reading from the table and tell the answer. So what a meter bridge consists of? Meter bridge consists of a wooden plank. It's a wooden rectangular plank. In that there is a 1 meter wire. So this is screwed in this thing. On top of this thing, you have a scale, a meter scale starting from 0 to 100. Well, it's a 1 meter thing. But what you can see in your meter scale is, you will see 1 to 100 this way, and each 1 to 100 opposite direction. So you can see two scales, 1 to 100. So this scale can be below this or above this. But you can see in one, it's 1 to 100 this way. Below 1 to 100. So you can see the two parts coming in the picture. So let's not do this now. Let's not draw it because this thing gets complicated. Let's not. So there's a scale there. Now, this is now you got a metal plate here. There are screws here, 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 here. So there's a gap here. So what we do is first we'll put a resistance box here. We'll put the unknown resistance here. And from here you connect a battery to a key. Now, a resistance box, if you see in your practical lab, it's a box. You can see a box. And there are some holes on that box. It's a wooden box. You can see holes there. And there are numbers written 1, 2, something, 50, 100, 200, up to 5,000 or 10,000, and there will be a point for infinity as well. So there's an infinity block here. So they have got some holes there with so much of resistance value written. And on top of it, there's a key closing the key. So you have got a key on that hole. So a key is, so you close all the keys now. So all of them are closed with a key. So first thing, if you're given a resistance box, check whether everything is closed. Press it nicely so that all of them should be inside that hole and nothing should be outside first. So checking whether they are all inside. And press it so that it won't have a confusion. So when you're given meter bridge practicals, first thing you do is check your resistance box whether it's intact. You press everything properly, give your good pressure, press everything up. And what we do is, we remove only one key out of it. And the key you wanted to remove should be the resistance you want to remove. For example, if I want to remove 10 ohm resistance now, there's a 10 written here. Remove that out. That means you remove 10 ohm, you put 10 ohm resistance here. So whatever you are removing from the key is the resistance you're putting here in this one. So all the other keys should be inside. The only one key you're removing should be the value you're putting. You can remove two keys also. If you remove 10 ohms and 20 ohms, the total will be 30. So whatever resistance you want to put, you can put it there. But remember, the resistance you are going to remove should not be very big or very small. It should be a value which is going to be in between. So you can't have, so better is after between 10 ohms to 50 ohms, you can remove properly so that you get a proper thing. Because why is that is if you remove small values, then the problem of the current flow in that will be affected. So remove logical values. So more than 10 ohms to 50 ohms you can remove now. So you are removing this. So this resistance is known to you. So you know what you are removing now, you know the value. So current from this battery will go like this. Will enter through this wire and this wire. And this wire is 1 meter wire, which is 100 centimeters. Now from center, there is another screw here. From there you connect a galvanometer. And galvanometer's got two screws here. So one screw will go to this, and one screw you connect a jockey. A jockey is a pen. It's a plastic pen type thing where you have got a plastic thing where you can hold it in your hand, and you got a metal small part so that you can touch. So this pen has to be used to touch the point. So this rope should be a longer one. This rope I can move from here to here. I can touch any part of the wire using the jockey. So jockey is now can be slided across this now. So remember now this wire should be a longer wire when you do this. Take a longer wire and you connect it. So once you do all the connections now, the first thing you have to be very careful is all the screw, every screw in everywhere, including the, I told you should press everything now, all should be tight, including the battery. So see to it that they're all tight. Once it's tight now, what you do, touch the jockey towards this end and this end, extreme edge touch. You see in a galvanometer, you've got a 0 at center and 30 values in the edge, 30, any value depending on the range. So when I touch the jockey at one end, my pointer will move towards the extreme side of one side. It will go out of 30, this side. If you touch it here, the pointer should go to this side. That means the pointer swings from here to here as I move the jockey from here to here. So when I move the jockey from here the pointer will go that side. If that's happening, then your connection is proper. You have done proper connection, you can start the practicals. So what you do now is very simple. Remove some resistances you want. Imagine I remove some 10 ohm resistance. So my R is 10 ohms. I remove 10 ohms now. Let's imagine I remove 10 ohm resistance now. I'm going to find the unknown resistance of the wire given to me, which I have no clue what the wire is. So what I do, I touch the jockey. My galvanometer will be at the extreme 30 position. I slowly move the jockey. What happens? My pointer starts moving. There's a 0 at center. So when I start moving slowly, maybe at some position, maybe at this point, when it reaches now, my pointer has now come to 0. Stop. This pointer is showing 0 means there is no current in the galvanometer. So there is no current flow between these 2 points. That means this point, say O and J, have a same potential. So no current is flowing. Stop it. You can see a scale. I told you what a scale is there. Scale ka reading you check now. Maybe this is 30 centimeters. This will be 100 minus 30, which will be 70 centimeters. You can easily find out 30, 60 or anything now. So because I told you there are 2 scales now. One scale starts from 0 towards 100, 1 0 in the opposite direction. So when you touch the point, whatever you see on the top is the 30 value. Just below it, you get 71. So whatever top you see is going to be the value. So this part I think is L, and this will be 100 minus L. So clearly, when you see the scale now, the top part of the scale, the top portion of the scale will give you L value. The below part of scale will give you 100 minus L value. So you can see the scale and tell the answer. You don't need to calculate what is 100 minus something, 100 minus 42 care. No need. Just on the scale of top and below should be there. Whatever starts with 0, that's going to be the L value. Whatever starts from 0 here, that will be the L value, 100 minus L value. Now, question is why is no current flow? So, we just studied just now in a Wheatstone bridge when P by Q is R base, no current flows. Wheatstone bridge have 4 resistors. Now, imagine there's a current coming from here, it branches into 2 paths, and this current is 0. So, there's no resistance here R. So, I got an R resistor here. So, let's make the resistance. Then we got the R here, so let's take R. We got an X here, let's take X. Niche here. This wire will have a resistance because it's a wire which is a resistance wire. This L will have resistance now, so there will be a resistance L of length L. Resistance, let's take P, and there is this part of resistance now will be Q. So this is resistance P, this is resistance Q, this R, this S, and each one is a galvanometer. And this galvanometer is not showing any deflection. So clearly it's a Wheatstone bridge. So meter bridge is having a principle of Wheatstone bridge, where there are 4 resistors now, each one is a galvanometer, but the galvanometer is not showing deflection. I'm very clear it's not showing deflection because your P by Q is R by S. So clearly my P by Q should be equal to R by X. R by X equals to P by Q. But P is a resistance wire. Formula of resistance is rho L upon X. So rho is the resistance of the wire. The wire is same wire, so rho will be rho only. L is the length I'm taking now. This length is there. This is 100 minus L upon A. A is area of cross section, same wire. So rho and A are same for the wire, but L is L. Below Q will be rho is rho only, but the length is 100 minus L upon A will be equal to R by X. Rho A gets cancelled. So L by 100 minus L equals to R by A. R by X. I know R, 10 ohms. I know L, which is 30. I know this is 70, I can find X. So X can be calculated from this equals to R into 100 minus L by L. So this gives you the unknown resistance which is given to you. You can even do 2 unknown resistances and put them in series and find out the law of combination of resistances now. That means you can put the first resistor X1 and find the value as 10. Remove it, put another resistor X2 and find the value as 20. And put them in series, your answer should be 30. Which proves that in series, resistance will be added up. You can do the same story for parallel as well. You can have X1 value 10 ohms, X2 also 10 ohms, put them in parallel, you get 5 ohms answer. So you can check whether your law of combination is also right by using meter bridge. And also you can find the resistivity of the wire. Because I know resistance now, use a screw gauge, find the wire diameter, and then you can find the area of cross section, pi R square. So find the diameter of the cross section using screw gauge, then find the radius of the wire. Pi R square you do find area. So I know, so rho your resistivity has to be found out. Resistivity is going to be Ra upon L. R is what I don't know. R is your X now. I already found out X now. Area is pi r square. You can find it using your screw gauge. L is the length of the wire. You can measure with the meter scale. So whatever wire is given to you, measure it first. It's the length. You can use a meter scale and measure it now. Some centimeters maybe. X is you're finding out the unknown distance over here, and use the screw gauge to find the radius and find the cross section area. So automatically you can find the resistivity over there. Once you know the resistivity now, check the value of resistivity from the table and see what the value is. If the resistivity is matching manganese, it's manganese. If the resistivity is matching nickel, it's nickel. If the resistivity is matching copper, it's copper, but copper cannot be used. Now, question is why copper wires are not used in your meter bridge? Meter bridge normally use wires which are high resistance wires, which is alloys, which is manganese, constant in nickel. The reason is why? Because they have a low temperature coefficient. So it's very important information now. We don't use copper, we don't use silver or aluminium. We use only alloys which are high resistance now because they have low temperature coefficient. What does it mean? Whenever you pass current, whenever you pass current because of resistance, there's a temperature increase. So with the increasing temperature, resistance also changes. Resistance and temperature are proportional. So as you pass current through a wire, because of heat, the resistance will be changing. Here, this whole experiment is based on resistance ka ratio. If it's going to change drastically, I will never get an answer properly because in every 5 minutes I get different answers. To avoid that, we are using manganese and constant thing, which says that they've got low temperature coefficient. That means with temperature, resistance won't change faster. They are not sensitive to temperature. So as you use your experiment for a long time, it heats up, its temperature goes up, but resistance won't change that fast. If you use a copper in that place, in every 3 minutes or 5 minutes or 10 minutes now, you get different answers now. So they are very sensitive. Copper has got a high temperature coefficient. And your manganese constant have got a low temperature coefficient. Semiconductors, which are non-ohmic devices, which don't obey Ohm's law, have a negative temperature coefficient. That means with resistance, with temperature, resistance goes down. So when temperature rises now, semiconductors will work properly. More current flows through semiconductor in case of so they are not going to follow Ohm's law. The VI graph is not a straight line. So semiconductors have a negative temperature coefficient. Alloys have a low temperature coefficient, and the silver, copper, conductors have a high temperature coefficient. This is something you should know properly. So we use a manganese or a constant wire because they got a low temperature coefficient. And even the sides of the metal bridge is the strips now, metal strips. Now, why do you use a strip? Why not a wire? Because this strip has got a bigger area. Because the area is big, resistance is always going to be less. So this part you connected now should not have any extra resistance to the circuit. So already there's a resistance here R, there's a resistance here X, there's a resistance here P, there's a resistance here Q. So only these four I wanted. I don't want any extra resistance to be added up. So to avoid that, these are made thicker so that there is no chance of any extra resistance added to the circuit now. Or in simple terms, we can say, or technical terms, we can say, the end resistance are avoided. So there is no end resistance in the circuit. That's the reason why your meter bridge always have thick plates on the sides. The last part of meter bridge I want to tell you, this is R, this is X, and this is your wire AB, this is a gallon meter, this is your jockey, this is L, and this is R minus. Now I'm first taking the value, so I got my R is something, my X is something. I got reading. I got reading as L and minus. So imagine this is 30, this is 70. Now what we do, I already got this value. Then what we do now, increase X. Now what will happen to the answer? Will my answer be more than 30 L side or less than 30? So understand one thing very clearly. Whenever I want to increase the resistance of this, my jockey will move in this direction. That means when this is increased now, L value will reduce from 30. So answer should be less than 30. Maybe 20, 10, something like that. But if I increase this value, my jockey will move in this direction, then the L value will increase. So my answer will be less than 30 when I increase this, will be more than 30 when I increase this. So always remember now, when I increase the right arm, it goes towards this side, L will decrease. When I remove the left arm, L will increase. When I say the change is 20 centimeters, this will be L minus 20 when I increase this. When I increase this, becomes L plus 20. So this is another information you should know, because changing the resistance on both sides will affect the balancing line on the different parts. Also, in a meter bridge, changing the position of galvanometer and your battery will not affect your balancing length. So in a Wheatstone bridge, if you interchange your battery and your galvanometer, in place of galvanometer put a battery, in place of battery put a galvanometer, then also P by Q is equal to R by XII. So there is no problem at all in doing questions based on that. So interchanging these two will not affect your balancing length. It's the next question. So this is what you have in meter bridge. The last part of the chapter is potentiometer. Potentiometer is basically, name itself suggests now it's based on potential. So it's not a same type like a meter bridge, but there are 4 wires normally we use in school. There are potentiometers with 10 wires also. So there's a 10 wire potentiometer, there's a 4 wire potentiometer. So we'll have a 4 wire for schools when we always have 4 wire potentiometer now. So the potentiometer, this is a board given to you. It's a wooden board with 4 wires. Once again, wire is made up of manganese concentrated because of low temperature coefficient. Now connect from here to a resistor rheostat. You know rheostat will keep the current constant. And then put your battery. The negative of the battery should be here, positive should be here. Then put an ammeter, which is a milliammeter, plus here, minus here, and then connect. So the connection should be like rheostat, battery, and then milliammeter. Then what you do, connect a voltmeter, then a jockey, and touch the jockey at point P. So when you touch the point P here, the voltmeter will show deflection instantly, because there's a current flowing in the wire from this I. This current is flowing here. So this I, voltmeter is a device used to find the voltage drop, measure the voltage drop, or potential difference between A and B. So voltage drop is IR. I is this. When I touch here, resistance of this part, AP, resistance of AP will be considered. So resistance AP into I. So my voltage I'm going to get is going to be I into resistance of AP. If I'm going to touch the jockey somewhere at Q, maybe out of this thing, I'll have a different answer. B equals to R AQ. AQ is longer than AP. So clearly, since AQ is longer than AP, resistance AQ will be more than resistance AP, because R is proportional to length. Since resistance is more than AQ is more than this, I is constant, your V2 will be more than V1. That means I'll have a more reading at Q compared to P. So as I move the jockey towards the right, as the length increases, because my starting length is from here, I start my measurement from here 0. So the scale will be from 0 to 100. So my scale will be from here to here is 100. From here it starts 101 to 200, 201 to 300, 300 to 400. There are 400 centimeter wire now. So my measuring point is here, because the current is entering it. Wherever it enters, my starting point. If you reverse ulta and make this connection here, this goes here and this goes here, this is my starting point. This is my starting point now. So starting point is the length is now, this is bigger. So as I increase the length, my voltage drop will be more and more and more. Or in simple logic now, the principle of potentiometer is always going to be your V proportional to L. But there's a small problem here. You cannot write V proportional to L in potentiometer, because there are some hidden problems there. So what you should write is V equals to IR. So we should know this first. And R is rho L upon A, so rho L upon A. When I say V proportional to L, that implies that V equals to KL. I got a constant value. So apart from L, everything should be constant. This is a constant. This is a constant value. If I want to write V proportional to L, then my rho is constant. Of course, logically, the wire is same. But my current and even A should be constant. That means in a potentiometer principle, the main points are this: a constant current flowing through a wire of uniform cross section, voltage drop is proportional to that. So if you do not write constant current and uniform cross section area, then V and L are not proportional, because then I and A are not constants, and you got a different answer now. So you have to be very careful now here that when you write the principle, the wordings are very important. A constant current and uniform cross section area. These are two keywords. A constant current flowing through wire of uniform cross section area. Your voltage drop is proportional to the length of the wire. So V is equal to KL is going to be the condition. This K has got a very significant information. KL. So K is V by L. K is called your potential gradient. So in simple terms, what is V by L? It's voltage drop per length. Or you can say voltage drop per centimeter. For every 1 centimeter, what's your voltage drop is going to be the K value. K value will always decide or help you to find out or increase or decrease your sensitivity of your potentiometer. Your potentiometer becomes very sensitive when your K value is small. So smaller K value is always better for a potentiometer. Smaller and smaller K gets is better and better for a potentiometer because they get more sensitive. Now, what does sensitive means? A sensitive instrument is the one which can measure small values. For example, a meter scale and a vernier caliper. Meter scale can measure up to 1 millimeter because least count is 1 millimeter. I cannot measure less than 1 millimeter in the meter scale. If I want to measure 0.5 millimeters, I have to go to vernier caliper because it's more sensitive. I can measure smaller values. Same thing, if you want to measure smaller values, your K value should be small. So let's give an example for this. I have 3 potentiometers now. My first K value is going to be 2 volt per centimeter. So K value is always in 1 centimeter was a voltage. So the first potentiometer has got 2 volt per centimeter as value. Second has got 1 volt per centimeter. And third has got 0.05 volt per centimeter. This is potentiometer A, B, and C. If I ask you what's the best potentiometer, I'll say C is the best one. The reason is simple. 2 volt per centimeter, that means this potentiometer, if you touch your jockey at 1 centimeter, I get 2 volt. That means I cannot measure less than 2 volt in the first potentiometer A. A can only measure up to 2 volt. If I want to measure 1 volt, I can't use that. Next one, I can measure up to 1 volt. And next one, I can measure even up to 0.05 volt. So it's very clear, my C has got a better prospect. It's a better instrument. So C is always the best one. So remember that smaller K value will be the better one. And K, B is IR and L is length. Now it's a very important information I'd like to tell you. So this what is L and what is R? So my resistance R is the resistance of the potentiometer wire. So any other resistance connected circuit is not going to consider. My voltage drop in the whole length AB is my IRB. And the length is going to be the complete length of the wire AB is going to be the value. So K value is all about voltage drop in the complete wire of potentiometer across divided by the length of the wire completely. If the wire is 1000 centimeters, you are divided by 1000. Because I'm going to get another L, which is the balancing length in small l. That balancing length is different from the complete length of the AB wire. So you got to be very clear when you use K, when you find K in the numericals now, it's going to be the I, the current flowing in the circuit, in the distance of the complete wire AB divided by the length of the complete wire AB is going to be the value. So how can I decrease it? How can I decrease it? Increase L. Simple logic. Increase the length of the potentiometer. That means instead of a 4-wire potentiometer, go for a 10-wire potentiometer. So if you're given an option to go for a 10-wire and 4-wire, 10-wire is the best one because 10-wire has got a more sensitivity than 4-wire potentiometers. So 10-wire potentiometers are much more sensitive than 4-wire potentiometers. The only problem, if you go to colleges now, colleges they have 10-wire potentiometers. The only problem is 10-wire has got a 10-meter wire with a wire which is made up of manganese or constant or nickel. It's a high resistance wire. It's a huge resistance there. So you need to have a battery with a high voltage. So you've got to be very careful now. 10-wire can be used, but voltage driven should be more so that you get a proper reading properly. So you need a high voltage for that to work. Otherwise, 10-wire is always the best compared to the 4-wire. So more the length better. But the problem in schools are we can't have 10-wire potentiometers now. You may have only one thing. So only you have a 4-wire potentiometer. Nothing will do with your potentiometer. Let's say. So L cannot be changed practically. So L, let's leave. So if you can't change L, how can I increase sensitivity? So I need to increase sensitivity. I need to decrease K. My L and R cannot be changed because this is already a wire connected in the circuit that's got a more resistance now. So whatever you have in your school, that's what you have to use. So resistance is fixed, L is fixed. If I want to reduce K, I should reduce I value. So if you want to increase sensitivity of potentiometer, you have to reduce K value. The best way to reduce K value is to decrease the current from the circuit. So put our resistance box in series, remove some resistances in the circuit, automatically your potentiometer gets more sensitive. So if I ask you, how can you increase the potentiometer, sensitivity of potentiometer without changing the length of the wire? By putting a resistance box in series and decrease the current in the circuit. So when you decrease the current, automatically the potentiometer will be more sensitive. So always remember now, K value should be small. So small K value is basically you can do it by increasing the length or decreasing current in the circuit. So what's the use of potentiometer? The first use is to compare EMF of two cells. You are given two cells now, you have to compare the EMF. So two cells given to you are Leclanche and a Daniel cell. There are two cells now, Leclanche, Daniel cell. And you can ask me a question now, why we need a potentiometer since we have a voltmeter also in hand. So question arises is, can voltmeter measure EMF? Or what if I put a voltmeter across my battery? What will it measure? The problem is when you connect a voltmeter across your battery like this voltmeter will measure the terminal potential difference but not EMF. You know, terminal PdV is always equal to E minus IR. So you cannot get the EMF value by using a voltmeter. So voltmeter cannot be used to measure your voltage EMF because voltmeter draws current. So if you ask me why voltmeter is not the right one, it draws current. So you cannot expect them to measure your EMF. So potentiometer is used because potentiometer don't draw current. That's the reason why they give a proper answer. So for finding EMF, potentiometer is preferred compared to voltmeter because voltmeter can only measure potential difference, the terminal PD, not the battery EMF. So I've got two cells I already told you. One is a Leclanche cell, another one is a Daniel cell. And for your information, E1 is Leclanche, E2 is Daniel. And Leclanche will have more voltage compared to Daniel. EMF of Leclanche is more compared to Daniel. So I've got a galvanometer. So in your books now, they have a resistance box here. This resistance box is used for only one reason, to save the galvanometer. Even if you don't put resistance box here or change the value of R, the balancing length will not be affected. So the resistance box connected to the galvanometer will only be saving the galvanometer, not going to affect your balancing length. So there's not going to be a problem at all. And I have told you, you've got two cells now, one is a Leclanche, one is Daniel. So if you see your Leclanche Daniel cell, it's made in school normally, they make it and give it to you. Leclanche has got a bottle, glass bottle is normally used, but you can use a plastic bottle also. And it's got a white colored crucible, like thing, white color. This is called a porous pot with a screw on top. So I have a white color porous pot which we dip inside the liquid which is there inside your this thing. This is called electrolyte now. This electrolyte is going to be ZnCl2. So that's an electrolyte used in Leclanche, ZnCl2. And you have a porous pot. Porous pot is there. And we use a zinc rod. Zinc rod will also have a small screw on top. So zinc rod and your porous pot has to be connected to galvanometer and resistor. First, you should know when you do the connections now, zinc rod will never go to the potentiometer. You should not connect zinc rod to this. Zinc rod should always be, it's always negative, it goes to the galvanometer. The zinc rod should be going to the galvanometer and not to the main circuit. So if you connect it the other way around, you will not get the answer. Your potentiometer won't work. You will not get balancing length at all because current is reversing and going now. You will never get the answer. So first note, you can easily make out what the Leclanche is all about. You've got a white colored porous pot and a zinc rod there with a ZnCl2 on the glass bottle. Why? Because the other one, which is a Daniel cell is a copper vessel. So you can always differentiate between a copper vessel and a glass vessel. It's got once again a hollow crucible, which is a white colored one. It's hollow, so you can pour something on this. So what we do? We pour diode H2SO4, and the electrolyte we use is Cu, copper sulfate. Copper sulfate is used, and diode SO4 is used. And you have a zinc rod dipped inside this, and you got a screw top on top of it. Once again, zinc rod should go to the galvanometer. So this part should go to the potentiometer, this side. Here the outside screw should go to the potentiometer, but zinc rod in both the cases should be going to the galvanometer. So that's the first thing you should know. You should not connect the other way around. So otherwise you will not get the answer at all. So first thing is that. Number one, precaution is that. So to see to it that they are not connected to this. Number two, this cell which is connected from here, this is called a driver cell. This driver cell should always have more EMF compared to these two cells. So this cell voltage should always be kept higher. So smaller voltage you keep, you may not get proper answer, you may not get answer. So if you want this circuit, this battery to drive a circuit, this battery should have more voltage. So it's always logical to have more than 4 volt, 6 volt, 6 volt is okay. It works properly. So see to it that this voltage is more. So when you have the connection done in your practicals, check this, what the voltage you're keeping. See to it that it's more, and check whether ammeter is working or not. Because if you have a galvanometer and jockey, even if this is not, imagine this ammeter is not working, you have not checked it. That means battery is not working. You touch a jockey here, deflection will be seen. Because this is once again another cell now which will show deflection. Now you may get confused. So I need this current. There's a current from here also. So what's the problem is this current should drive. So if this is not working, then you will not get the answer properly. So ammeter, you check whether it's working properly and see to it that this reading of the ammeter should be more than 100 milliamperes for getting an answer properly. Less than 100 milliamperes you may get the answer, but it's always better to have more 100 milliamperes and more. So always rheostat, move the rheostat and keep a value first more than 100 milliamperes. So you start say 120 milliamperes. You have different currents. My current first one I take 120 milliamperes. And what I do, I'll close this key. That means this will work, this won't work. So when I touch this key and touch the jockey now, the current from this will also be moving, I1. There's a current coming from here. These two currents will go together. And this will have current I1 coming back, and I will go this way. Because this galvanometer is going to show deflection because of I1. So when I touch the jockey here and I start moving the jockey slowly, this galvanometer will show deflection from one end to another. That means the galvanometer deflection will start from the maximum. The T side will be somewhere here. It starts moving towards 0. Like what we did in your potentiometer meter bridge now, once you correct the correction now, touch the jockey at this side and this side. The galvanometer deflection should be an extreme end now. That means you're right. Proper. Then you start moving the jockey slowly. The galvanometer will start showing deflection from maximum to 0. At one point it will show 0. Question is, why is the current going down? Why is the galvanometer becoming 0? Let's find out that. Imagine my potentiometer, my galvanometer is connected, and this thing is connected here. Jockey is here. The current will go like this, enter this much of the wire and come back. That means the resistance I'm putting is this much for this loop. This loop by resistance R is this. When I take somewhere here, my resistance is increased. That means in a circuit, when you put more resistance, current decreases. So this pointer is now going towards 0 because as I get the jockey positions from here to here to here to here, I'm increasing the length of the wire. That means in this circuit, I'm increasing the resistance value. Since R is getting bigger, current will get reduced. So at one point, it shows 0 deflection because I have to reach this point. And when are you getting the 0 deflection? Because simple logic. Once again, as I move the jockey, the voltage drop because of the current I is now getting bigger and bigger and bigger. So here the voltage drop may be say 1 volt, 2 volt, 3 volt, 4 volt, maybe it's increasing. At one stage, imagine this is 10 volt. It's never 10 volt, don't worry, I'm just saying the example. And I'm touching the jockey here, it's 1 volt, 2 volt, 3 volt, 4 volt. At one point, I got 10 volt. All the 10 volt is got dropped. This 10 volt, in this point, this is 0. All the other volts got dropped. So now this is 0 volt. ये 10 volt था because this is 10 volt point, and this is now all the 10 volt got lost. 0 volt है, AB 0, AB 0. So there will not be a current flow in this one. That means whenever the voltage drop in this length equals the battery EMF, because I'm moving the jockey slowly, the resistance gets bigger, the voltage drop also gets bigger. This voltage drop matches the EMF E1. There will not be any current flow in the potentiometer. That's called the balance condition of your potentiometer. We can say it's balance condition. We can say balancing length, of course, and balancing length is small l. So I told capital L is for the complete length of the wire AB, and then I get a small l value. So my E1 will be the voltage drop on the first one. R is rho L upon it. So rho is rho only, I told you. L is L mark. This is my E1. So I just put the value of E1, I got the voltage drop. So what we going to know now is we get the balancing length because the voltage drop in that part is equal to the battery voltage, EMF. So we got the answer. Similarly, now remove this key, put this now. So you got E2 will be equal to IR2 because the voltage drop in the second is matched. R is rho L2 by A. Now E1 by E2, everything is cancelled. Only you got L1 by L1 is calculated by you, L2 is calculated by you. Divide them. That's going to be the ratio of EMF of E1 and E2. That's what we want in your potentiometer for comparing in two sets. Always we take 3 readings for L1, 3 readings for L2. The readings are taken but change the current value. So first 120 milliamperes take L1, 140 milliamperes take L1, 160 milliamperes take L1. Similarly, do the same thing, say 120 for L2, 140 for L2, 160 for L2, and take the mean. So this is what you do to find the EMF of two cells. So first of all, in comparing EMF of two cells now, you get a balancing length only because the voltage drop in that part is equal to the battery EMF, the EMF of the cell type. Now the next part of potentiometer is to find the internal resistance of the cell. I can find the internal resistance of the given cell. I can find the resistance of my Leclanche and Daniel cell respectively. So what I'll do, I'll put a Leclanche cell first. Galvanometer. I can put a resistance box if I want. You can put it if you want. I put another resistance box here. This is very, very important. This resistance box has to be important taken now. There's a key here. Okay. Now this is what I need. So this is my Leclanche cell first. There's a resistance box here. I can remove any value I want. You can put resistance box here also. And as I told, this is not going to affect your answer anyway. And then this is a key. Now what you do, keep your key open. So that means there is no chance of this part working. It's open karoge. Current from here will all go to this one. Nothing will go to this because it's open side. So all the current will go to this. So my E will proportional to L1. E is IR1. So all my current goes, all the voltage drop will be equal to EMF. The 10 volt will go. Now keep the key closed. Now when you close your key K, some current will branch out for this as well. All the current is not going. So the current flow is not the same. It's going to be reduced now. And some voltage will drop in this. So all the voltage of EMF is dropped, not here, some part is dropped here. So my V will be proportional to L. So this is my terminal P. So E will be proportional to L1, V is proportional to L2. So E by V will be equal to L1 by L2 is what I get from this equation. Now the very important information you should know is your L1 value should be more than L2. That's number one. Number two, the resistance you remove here is also very important. If you remove resistances like 1 ohm and 2 ohm, then L1 L2, the difference is very big. That means if L1 is some 300, L2 will be somewhere at 250, 220. So there's a huge difference now coming into picture. More than 10 centimeters. But if your R resistance you remove is 200 ohms, big value, then L1 L2 will be almost close to each other. The difference may be 1 centimeter, 2 centimeters away. So L1 L2 value, you can check how it's changing when you do practicals now. So if you remove small resistances now, L1 L2 will have a huge gap. If it's big resistance, L1 L2 is closer. And L1 should be more than L2. Otherwise, you make something wrong in your calculation. So that's a condition. Also, you know, small r value is always going to be small r. For example, if you have a battery, you have a resistance R, EMF, and R. If I ask you what's the current now, current I equals to E by R plus R. E by R. And voltage drop E is equal to IR. Instead of I, you put E by R plus R into R by V. Take this R plus R here. R plus R will be E by V into R. So small r will be E by V into R minus R. So small r will be E by V minus 1 into capital R. So small r, this is a formula now. E is EMF, V is terminal voltage, R is the resistance you remove now, and small r. So E by V value can replace R L1 by L2. So L1 by L2 minus 1 into capital R. This is the formula for internal resistance to be found out by using potentiometer. L1 you calculate, you already get the reading. L2 you take the reading. R1 you remove it anyway R. So small r can be calculated, and logically you know small r is very small, less than 10 ohms away. So this is what you have to do in case of your potentiometer. So this chapter has got part 1, which is based on series, parallel, terminal voltage and all this stuff. And part 2 is based on Kirchoff meter bridge and all this. So this completes current chapter. So we have done almost everything in this, and the only problem is this chapter has got lots and lots of numericals now. So try to do topic wise. That's the most important thing, and for that I'll give a video for only one topic, which is your Kirchoff's law separately and meter bridge separately, like that, so that it's easier to do numericals on that. Before we finish and before I say bye bye, as usual, we will go for the summary of this chapter.
So guys, let's check the summary of current electricity part 2. Kirchoff's first law is based on law of conservation of charge. Kirchoff's second law is based on law of conservation of energy. In Wheatstone bridge, by interchanging battery and galvanometer, the balancing length will not get affected. Manganese or nichrome wires are used in meter bridge because they have a low temperature coefficient. By increasing the resistance of right arm of the meter bridge, the balancing length L reduces. By increasing resistance of left arm, L value increases. The driver cell of potentiometer should have more EMF than other cells. Smaller the value of K, more sensitive will be the potentiometer. K value can be reduced by increasing the length of the potentiometer or decreasing current.